Yeah, I know. See, I think I read it.
No swear.
Okay, just checking. No, I'm
X.
I knew.
Okay,
That was beautiful.
isn't that good?
Is this the beginner's version of string theory? The chain rule?
Well, it's, it all leads to string theory.
All leads to string theory.
Are we gonna learn string theory?
You're gonna learn string theory.
One graph little figures.
There is no learning of string theory. There just is string theory.
Okay, so the chain rule. The chain rule is huge. The chain rule takes everything we've done and makes it better.
No,
Way better. It allows us to do things like now what we know is just so limited anyway. We can do things like this. We could take, if we knew y equaled sine x, we could find y prime, right? Big deal. That's just sine x. What if we wanted to deal with instead something like y equals sine of, let's say we're going to do x squared plus 3x minus cosine x.
You're adding no. That's a no.
We can do that, right? We can do functions of functions. That's what the chain rule allows us to do. Okay, the chain rule is everything in calculus. We have some basic rules, but those basic rules are super limited because we can only deal with this specific exact form. We can't even do this. We can't even deal with like sine of x squared, right? Okay, so the chain rule lets us do all that stuff, right? I want to give you a little kind of a model to use that we'll come back to that I think works pretty well for the chain rule. So let's think about, what if we define let's use a clock. Okay, an analog clock. So for an analog clock, let's go ahead and let's let S equal the angular position of the second hand. Let's let M equal what? Angular position of the minute hand. And let's let H equal the angular position of the hour hand. Okay? So I want to know what is ds dm. Talk about angular position. What do these hands do on a clock? Like that, right? They turn, no, they turn counterclockwise. No, they don't. They're clocks. They turn counterclockwise. So,
In calculus, they turn counterclockwise.
okay, so yeah, they just turn, right? So their angular position is they just go around in circles. Okay, so what does this say? The SDM. Okay, yeah, it's a derivative. You're right, and it is a derivative. But
It's the tangent.
we want to think of it in terms of probably a rate here, right? So derivatives also represent rates, as we've sort of talked about a little bit. We'll talk much more about it soon. If I want to say this as a rate, I would say this is the rate of change of S with respect to M, or what do they stand for? This is the rate of change of position of the second hand with respect to the minute hand. Okay? So I want a number out of this. Can you tell me a number? Okay. The word 60 is an important one, isn't it? Now, the suggestion was 1/60th.
Not the 60.
Okay, so what do you think it should be?
60 over 1.
It's 60 is the answer. How come? Right, how come?
There's 60 seconds in a minute.
Okay, and another way of thinking about that is, for the second hand to go around, or for the minute hand to go around once, the second hand has to go around how many times? 60. Does that make sense? Okay. Okay, so that, in other words, the second hand is moving 60 times faster than the minute hand. Everybody agree? Okay. So what is dm dh? No, it's not 60.
24.
Think carefully. No, not 24.
It's a weird fraction. So you're
360.
No, here, I guess you guys, you're not used to analog clocks anymore, are we?
24 divided by 6.
Well, I don't have one in here.
I'll give you a picture when we
Point
look
four.
at it.
cool.
Point four. Let's go with point four.
It's a decimal.
Point four.
2 minutes.
Now we're just like,
2 minutes, 35 hours.
we live in the digital age. Nobody looks at
Well,
analog clocks.
You're right.
Something to look at in here. You have like a TV from the 70s, but then you
You just need a little disco, huh? Or not?
Oh, just
Oh,
would be
would you be
24.
one?
Just be 24. No, just be 24.
No.
24.
Look at this picture,
24,
come on,
12.
come on now.
12.
You guys are being ridiculous, come on.
We're calculus students, not philosophers. We're historians, not historians.
Whoa.
Tick tock.
Check
the
that
clock.
out.
Whatever
Check that
stuff.
out. Okay. So there's our analog clock.
Our battery.
Which hand is the second hand?
The red one.
The red hand, which is the minute hand.
The long one.
Okay, and so the short one is the hour hand.
Yeah.
So I ask again, what is dmdh? What's the rate of rotation, we'll say, of the long black hand compared to the short black hand? How many times faster does it move?
Oh, gee whiz.
Think in terms of
I
numbers
know.
of rotation.
Yeah,
Just
I know.
ask yourself the simple question, how many times does the minute hand have to go around for the hour hand to go
72.
around once?
100.
One.
720.
No.
720.
Because, wait, don't clocks work like, no,
Now, are you serious, you guys?
never mind.
Is this?
Like, I know how to read
I
an
didn't
analog
intend this
clock,
to be that
but-
hard. How many hours does it take for the hour hand to go around that clock once?
One.
No, the hour hand.
Oh, 12.
Yeah.
12.
That's what I said.
So what's the answer?
12.
12. I didn't even
I
say
said
it.
that so many times. I looked at your face and said that, and you looked at my face and said no.
I don't think so.
Yeah, no, that
No,
happened.
he
No,
did.
you said
I did.
24.
Yeah, and then I said 12 after that.
Oh, you did?
Yeah.
Oh, okay. Well, I was-
No. But to be
Wrong.
fair, you were throwing around so
Wrong.
many numbers, you probably stopped
Yeah, I
listening.
I mean, yeah, that's a good
Now,
point.
is it, so,
Wait, so,
is it, so would the 61 be 60 because there's 60 minutes on a clock, not there's 60 seconds in a minute, then?
Stop thinking
It's,
about it.
well, it's,
Don't worry about it.
No, it just,
No, you
how I
need
thought, how I
no,
thought it was
you're,
explained
that's right.
was that, because there's 60 seconds in a minute. But if it's 12, because there's 12 hours.
It's because there's 60 minutes on a clock, that's
Oh,
why it is,
okay.
you're right,
Okay.
exactly, that's
so
why.
you look at the bottom.
Yeah, because you're asking yourself,
How
how
do we
many
get
revolutions does the second hand have to make for the minute hand to make one? And that's 60 because there's 60 minutes on a clock. This is 12 because there are 12 hours on the clock, right? Okay, but really, this doesn't seem right, does it? But this is true. The minute hand only moves 12 times faster than the hour hand. See, it doesn't seem right, does it? We should think about it. It seems like it'd be more. And the second hand is only 60 times faster than the minute hand.
Only
Yeah.
60.
But that's a lot. Okay, but here's my next question then. My next question is, what is DS
720.
DH?
720.
And the answer is 720. Okay, why? The answer is the chain rule. Because DS DM times DM DH equals DS DH. And you can literally think about this as algebraically canceling those. Okay, as long as those factors are the same, we can treat this just like we would any fraction. Okay, but it's more complicated than that in a way, because these actually could represent functions. Okay, but that's how the chain rule works. What it allows us to do is it allows us to take derivatives of a quantity with respect to one quantity and link that to a different derivative in such a way that we can link those two, right? Okay? So we'll come back to this idea, but just hold that thought. This is a good model for the chain rule. If we write the derivatives in ratio form, right? But we got many ways to write derivatives, don't we? Right? We said that, there's just an embarrassment of riches when it comes to ways to write the derivative. We know that f prime of x is the same thing as dy dx, for example. Those are the two most common ways of writing it. We write it in function form, or we write it in ratio form, okay? And they each have their values. I mean, it depends how you want to look at it. Okay, let's look at a different kind of problem. Let's look at a problem like, how about, something like this? What if we've got the derivative with respect to x of, which one should we do? We'll just do sine 2x. Okay. That's the derivative of a function of a function, right? So we need a rule for that. This is kind of the other way of looking at the chain rule. So the other way of looking at the chain rule is if we're going to take the derivative with respect to x of f of g of x, what do you think we're going to do with that? Okay. We're going to have to ask ourselves, like the clock, what's the rate of change of f with respect to g, but then also, what's the rate of change of g with respect to x, right? What did we do before? We looked at the rate of change of the second hand with respect to the minute hand, but we also had to consider what's the rate of change of the minute hand with respect to the hour hand, right? And we had to multiply those two rates together, okay? So what this is going to give us, this is the chain rule written in the way you'll use it most of the time. This is going to give us the answer f prime of g of x times g prime of x, okay? That's looks kind of clumsy though, doesn't it? Right? Having that extra function inside of the f of x clutters things up visually. So one good way to represent this that we do in calculus is we say, okay, to make that easier, let's do the same thing, but let's just make this substitution. Let's let u equal the function g of x. We don't have so many nested parentheses and things, but it stands for the same exact thing, right? So if u equals g of x, how would we write, for example, g prime of x? U prime, right? So then we can make this a simpler form here. We could say the derivative with respect to x of, yeah, be careful with this, f of u, okay, we'll be careful with that all year, is equal to f prime of u times
U prime.
prime.
U prime.
Right? Okay. So now we could do our, that's not that hard, right? That makes things relatively simple, but it expands our ability to take derivatives tremendously. So in this first situation, what's u? Sounds like I have bad grammar. What's u? It's 2x, isn't it? Right? So if u equals 2x, then what's u prime? 2, right? So the answer to this is just gonna be the derivative of sine of hand. What's the derivative of sine of hand?
Cosine.
Cosine of hand, right? So we're gonna get cosine of hand, which is u, right? Times the derivative of hand. So the derivative of u is 2, right? So we get cosine 2x times 2, and that's our answer.
Yeah.
We'd simplify by putting the 2 out front, but that's our answer. That's the calculus part right there. So how do we sort of turn that into a process? Really all you're doing when you apply the chain rule is you're just peeling the layers of the onion, right? Derivatives are complicated, like ogres. They have layers, okay? So, and onions, right? We gotta peel them one layer at a time, right? So we're gonna start on the outside and we'll take the derivative of the outside layer and then we'll work our way in. And in doing that, we could actually do pretty complicated derivatives,
So would we just keep on doing it? It was like.
multiple layers. In fact, I'll give you one right now. You guys will be surprised. You can already, just knowing that, I bet you can do a really hard problem just by following that idea. Like, for example,
This is like long division, yeah.
it's kind of like long division.
Long division is simple.
So,
Yeah, I know, this is just simple, it's complicated. It wasn't simple back then, like it was, but like this is simple still.
okay, so
So it'd be simple less than that.
let's try this. What if we've got, how about,
I'm ready. I'm dead. I don't know.
We're using bonus now.
Is that why you probably would do calculus?
You always
have
down
to
so you
like
get
that.
on.
yes.
Yep. Accurate.
Okay, let's do,
Okay, I think I know where we're going here. I think I got an idea.
Okay.
Oh, no, already lost.
What is-
Oh, that's cute.
Yep. I think.
Sine is cosine. We got
Yeah.
Talking about Michelle, trying
No,
to
it's
sabotage me.
right.
Sabotage her.
okay. So let's say there's our function that we want to differentiate. Okay, so the first thing you definitely want to do here is we want to write it, write it down, but we want to write it maybe in a slightly different form. We want to write it in the form where we can see the layers better. So for example, tangent cubed of hand is shorthand for what?
times tangent.
Right, so it's the quantity tangent hand cubed, right? So let's do that, let's rewrite it that way. So it's gonna look like the quantity tangent of sine of 2x plus 3 to the 4th
I'm just gonna write this out 3 times.
cubed, right?
Cube. Yeah.
Okay.
Yep.
And so now we're going to peel the onion one layer at a time. So the derivative. So we start at the outside. What is the outermost layer? What are we looking at here?
So you can't do this.
Okay, but what is,
Or-
no, it's not.
Okay.
What is the outermost layer? How do I look at this? What rule do I apply at the outside layer?
Exponent rule.
Exponent rule, it's a power rule.
Oh.
Because outside, I've just got hand cubed. I don't even need to look inside. In fact, don't, it's confusing. All we're looking at is what's the outside rule. The outside rule, at the very outside layer, this is a power function, right? Something cubed. And so the first layer is gonna be, what's the derivative of hand cubed?
3 and squared.
3 hand squared, right? So the outermost layer is 3 times hand squared.
Now, would you do it as y?
Sure, just what do idea, whatever you wanna call it. This is the function and we're taking a derivative.
And then would you do the next one, like as the y and then
By 2 prime.
Y double prime, yeah, would be the second derivative. But, I mean, we're only doing a first derivative here, right? That's all we're doing, we're just doing a complicated one. So, once again, you notice I didn't even write in what's inside there, because I don't want to contaminate the process, right? The first layer was just something cubed is equal to 3 times something squared. Well, now we can go back, now that we've done the first layer of the derivative, we can go back and fill in what's there. So it's a tangent of sine of 2x plus 3 to the 4th, right? Brackets. Okay? All right, so now that we've peeled away the outside layer, I'm just going to do this. Let's just kind of, so that's gone. What's the next level? It's a tangent of something, right? What's the derivative of tangent of something?
Secant squared.
Secant squared of something, right? So the next layer looks like times, whoops, times secant squared of something, right? Okay, the derivative of tangent something, tangent hand, is secant squared hand, right?
Don't you still need to write
Yeah,
the
wouldn't you-
bracket 3 squared?
What do you mean? That's right there.
No, like, the 3 on the outside and the second power.
Yeah, on the second.
No, because remember, it's f prime of u
Mhm.
times u prime, so if you were to expand that out, it'd be like the g prime, and then we're going to have an f prime.
Okay, so
and then
if
a
we went
4
back,
primes.
right, if we went back to the previous page, look what we did. We said f prime of u times the derivative of what's inside, right?
Well, wouldn't,
So
Yeah.
what's inside now, the cubed has gone away. So now I've just got the tangent of something, right? I don't care what's in there. It's just the tangent of hand. The derivative of tangent of something is just secant squared of that something, right?
derivative of something.
Right? So the next layer, the derivative of tangent, gave us back secant squared of all this stuff. Sine of 2x plus 3 to the 4th, right? Okay, so we peel away the tangent layer. So now the tangent is,
We need a bigger picture to-
right, is gone, okay? What's the next layer we expose?
Was it, is it sine?
The sine.
Is it the
The sine.
Wait, would
Right.
it just
4?
be the,
Would it be the sine of the 4?
No, it's the, oh, actually, yeah, hang on, it's the 4th, isn't it, right? Because we'd wanna, no, it's not, it's the
No.
sine, because that 4th is, there are some implied parentheses here that we really should add. The implied parentheses are right there, right?
Whoa.
Right?
Those are implied.
Yeah, they are, because this, right? If I've got the sine of x squared, that's not the same thing as sine squared x, right? Sine x squared implies that. Sine squared x implies sine x quantity squared. See the difference? Okay, right, so write the implied parentheses in.
Yeah, so many parentheses.
Okay, so,
But if it was sine 4 2x plus 3, then it would be sine.
okay, so then the next layer would be the derivative of sine hand is what? Cosine hand. So we got cosine hand, right, which is 2x plus 3
that's just
to the 4th, right? So we peel away the next layer. We peel away the sine layer, and now what have we got?
4x.
Not enough room for
4
your equation.
times 2x plus 3 cubed.
Yeah, now I've got hand to the 4th, right? The derivative of hand to the 4th is,
This looks like it's gonna be really fun to multiply.
what's the derivative of hand to the 4th?
4 and
4 hand cubed. So times 4 hand cubed, and hand is just 2x plus 3. And so finally, what's the derivative of the inside layer of the onion?
5.
2.
Shut up. I
Okay.
just broke my tooth.
And so that's our answer. Now, how many links are there in the chain?
So
for the chain rule?
5.
How come there were
That's where I
5?
got the 5.
How many layers were there to the original function?
There are 5 layers of each.
5 layers. So there are 5 links in the chain rule, right? 1 for each layer. You differentiate once for each layer, right? And so to simplify this, it would be kind of a mess, but actually we wouldn't have to do very much. We'd pull the 2 and the 4 out front, and so if we wanted to write this as one big function, we would just have 24, probably put that next, 24 times the quantity 2x plus 3 cubed times tangent of that mess times secant squared of that mess times cosine of that mess. That part we wouldn't really change, right? We'd write that maybe as tangent squared. We'd put the 2 there, but make sense? Okay.
So for the answer, or is it not worth finding what the answer would be right now for us?
Oh, no. I mean, that's the answer.
Like, that's what we would plug into.
Well, yeah, I mean, you would just kind of put the trig functions, those trig function factors at the end, but that's it. That's your answer to the derivative. That's your answer. Okay? But the point is, even a super complicated problem like that, the process isn't that bad, right? You just gotta start on the outside and work your way down, okay? All right, so how would I deal with then something like, let's just take some more mundane examples. How about things like this? How could I do? I don't know, what if I had y equals the square root of 3x squared minus x plus 1? How do I find y prime?
All that's gonna be x to the negative 2.
Well, okay, so I'd wanna rewrite the original probably. How?
Do it all
Change it
to
to
the
the-
negative 1.
The quantity.
To the- Okay, yeah, square root is a 1/2 power, right? So we'd write it like the quantity 3x squared minus x plus 1 to the 1/2. And then at the outside, it's just the power rule, right? Something to the 1/2. So what's the derivative of something to the 1/2?
1/2 times negative.
Something to the minus 1/2, right? Times derivative of the next layer.
What are we gonna?
What's the derivative of that?
6x minus.
Yeah, they'd have to put that in parentheses, right? That's it. I could clean that up. I could write that as, let's see, I could write that as 6x minus 1 over 2 times the square root of 3x squared minus x plus 1, right? If I just rewrote that. Make sense? Okay. How about... Okay, what about something like this? What if I had f of x equals, here's a problem we can do right now. But now it's a pain, right? To do that derivative, we would have to, without the chain rule, we'd have to expand that whole thing out and differentiate term by term, right? Right? How can we do that with the chain rule?
One layer by layer.
What am I gonna get?
3 times hand squared.
Yeah, 3 times hand squared times
3 minus 4x.
3 minus 4x, right? Now, I mean, if I want to simplify that, yeah, I still got some work to do. But a lot of times, the derivative doesn't need to be simplified, because if we're using it to find values of, values of the derivative, I can just evaluate the function at various powers of x, and why do I need to simplify it if I'm doing that? just plugging this expression into a calculator and substituting values of x into it, right? Okay? All right, how about something like this? What have we got? Let's say, tell me how you would do that problem. Think about it for a second. Yeah. Everybody see that? Okay, so first of all, there's two important things we gotta remember here. Do we wanna use the quotient rule? No, and why do we avoid the quotient rule like the plague here? Because it sucks, but why is it, what about this?
It's a very long process, that's very.
It's a very long process, but what allows us to not have to use the quotient rule? Why is this not a quotient?
Because you can rewrite it as multiplication.
Yeah, good, because we can rewrite it as multiplication, and in this case, because the top is a constant, right? So we'd always rewrite this as just a negative power, right? So we'd rewrite this as -4, which is a constant, times 2t cubed minus 1 cubed, right? And now I can do this derivative because I've just got hand cubed. Negative, right, negative, you're right. Okay, the -3, okay. Make sense? Okay, so then this allows us, you took my word for it, but let's show that I wasn't lying to you. Let's,
We trust you.
oh, no,
Yeah, we
you
trust
don't
you.
wanna trust me, I've got too many things up my sleeve, you don't wanna trust me. So what if we wanna prove here that, we're gonna, how could we do that? I just told you the answer, but how could we find out what the derivative of secant really is?
It's 1 over cosine.
Okay, so we write it as the derivative with respect to x of 1 over cosine, which is the same thing as
Cosine x to the -1.
cosine x to the -1. Yeah. Okay, well, now we can do this. We couldn't have done that before, but now this is easy with the chain rule, right? So what I've really got here is just hand to the -1. So what's the derivative of hand to the -1? Negative, good. Hand to the -2, right? Times what? Okay, so if we clean that up a little bit, that's gonna give us minus times minus is plus, right? And we're gonna get a sine x on the top and cosine squared x on the bottom, right? Okay, so how could we split that up? Well, we could just write that as a product of sine over, as 1 over cosine times sine over cosine. And what's that?
Secant times tangent.
Secant x tangent x, how about that? Okay, so we got it. Okay, so I wasn't lying that time, okay? What does this allow us to do with all of our standard forms? Okay, this allows us to take these kind of lame derivative rules that we had. Like, for example, we had the derivative rule, the derivative with respect to x of sine x equals cosine x, and now we can rewrite that in a better way. We can rewrite that as the derivative with respect to x of sine u equals what? Cosine u times u prime. So that's the general way. If you look at derivative tables in your book, or online or something, those are the ones you're gonna see, because these are the ones that allow you to take the derivative of the sine of a function, right? A function of x. Now, what if u is sine x? Well, then this just devolves, right? This collapses down to our original formula. If u equals sine x, then we're just gonna get cosine x times the derivative of x, which is what? 1. Okay, make sense? All right. So then what would, for example, the derivative with respect to x of u to the n become?
And just u and minus 1
Times
u.
Make sense? Oh, the other form of this then, that sometimes is useful. So we've got the form that I gave you back here, right? Okay, we could write this in ratio form similarly. We could say that, let's see, d y, if y, we're saying y equals f of x, right? So dy y equals f of u, sorry. Okay, then dy dx equals what? D what times d what dy.
X over U.
Y over u and du over x.
Yeah, because isn't that just that? F prime of u is the same thing as saying dy du, right? Okay, times
U over x.
du dx. And there's our clock example, right? Okay, how much time we got? 4 minutes.
I like this. This is fun.
Mm-hmm.
This feels like long division.